Uh, Hello, class. I hope you're doing well. I hope you guys have been keeping up with your studies because, like how UBC is. Actually, you might not know because it's your first year. Yeah, it picks up pretty quickly, and then when you're behind, it becomes very difficult to catch up. So, today we're gonna actually talk about. So last class we talked about. Um, we talked about ionic bonding and metallic bonding, and then lattice energy and those type of informations. So today, we're actually going to talk about covalent bonding, polar covalent bonding, non-polar covalent bonding, and hopefully Lewis structure. And then I'm going to give you a bunch of tips how to do these questions quickly. And yeah, so hopefully it's going to go well. And you guys are going to learn a bunch of new things. So I'm very excited about the Lewis structure part because it's very important. You will be needing it in chemistry 123 and all the way to other courses. And if you're struggling with it, pretty much you can't do anything in chemistry. And you also need to be able to do it quickly. So it's just not a matter of knowing how to do it. It's a matter of knowing how to do it properly. So let's talk about covalent bonding. So covalent bonding is actually one of the, maybe not one of the, it's actually one of the strongest bonds in the world. So it's actually very strong, and it's usually between atoms that have relatively similar electronegativity. So remember, if they're too different, that makes it ionic. And we already talked about which ones do ionic. So it's pretty much not metallic ones, not transition metals, and not the group ones with those guys. It's pretty much like everyone else. By the way, when we're talking about group 1 and 2 interacting with other guys, I was not talking about hydrogen. Hydrogen is a huge candidate for covalent bonding. You can do hydrogen ionic bonding, but not usually. That's not as far as you need to know for this class. So before we talk about something, we'll be talking about that. Something that is actually very important is that you must have seen it in class too, that when you're making the bonds, there's a possibility for a single bond, double bond, and triple bond, as you might think. So there can be a carbon, which is a single bond, let's say, or a carbon-carbon double bond. Again, the fact that it's a carbon is just an example. Or a carbon, let's actually draw a little bit more organized. So carbon, 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 and then carbon, 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 carbon. So it's actually single, double, and triple. So you're like, okay, so what about it? Well, first of all, when the bond is just a single bond, we call it the order, we just call it first order, or second, or third. And if you're wondering, okay, why the hell is it this type of naming? It's just different way of naming something. So this is not a big deal. So first order, second order, and third order, so that's what it means. When you say a bond is second order, it means it's double bond. So, but that's not really the main point here. So you see, as you go from a single bond to double bond to triple bond, and back, we need to talk about their lengths and also the strength. So the strength you probably can actually guess and say that, well, I mean, well, this one is like 3 of it, this one is 2 of it, this one is 1 of it. It's actually, first of all, it's not like the double bond is not this times 2. The second one is not as strong as the first one. But I mean, there is some cumulative effect on it. So it's going to be like the first one plus something and plus something. So when it comes to the bond strength, if you're going to rank them, this would be first, this would be second, and well, let's say like let's rank them. So this would be bigger, and then this would be bigger. So yeah, so triple bond would have been bigger, and then the double, and then single. But then the other factor that you want to actually talk about, like for the bonds, is actually bond length. And you see, this is actually, well, the stronger the bond is, the closer these guys to each other. So it makes sense that the strongest one actually has the smallest length. So that's why it's actually the opposite trend. So you see, this is actually pretty straightforward. Like you can see, easy. So that's it. That's for this part of it. Now, let's actually talk about covalent bonding a little bit. As we said, in ionic bonding, there's like a bully, and then there's one that actually gets bullied. The one that is like more electronegative is so much more electronegative than the other one, where it actually takes it out. So it takes the electron from the poor guy, and so that guy that loses the electron becomes positive, and the bully becomes negative. Here is actually not so much. Since there is like a more balance between the electronegativity of the two, that's why they're going to be closer. And there's not going to be, there might be someone, and so they're going to be sharing. Maybe it's not going to be an equal sharing. Maybe it's going to be an equal sharing. And we're going to talk about that in terms of polar covalent bonding and non-polar covalent bonding. So you see, now we're going to actually talk about those two guys actually. So again, just for your information, we're going to mention it. So you have this right here. The electronegativity increases in this direction, because we're going to talk about electronegativity a lot today. We talk about electronegativity almost every topic when it comes to drawing resonance structures and such. So it's very important. So you should like know this by heart after like practicing a little bit. So anyways, when you're talking about when it comes to polar covalent bonding, it's actually it's a bonding between two atoms of different electronegativity. But then you wonder, well, I mean, I don't have it memorized. Are they, so can we actually just argue that every time that they're actually just different compounds, they have different electronegativity enough for me to create an imbalance between the two, like when they're bonding to each other? The answer is almost yes. So you see, when you're actually bonding these guys to each other, as I told you, these are metallic. These guys, when they're reacting with these guys, it's going to be ionic. And then when these guys are interacting with each other, like all of these guys, plus hydrogen, it's covalent. So But then you have to wonder, okay, is it going to be non-polar covalent or covalent, polar covalent? And the answer is very simple. You see, all the atoms here have different electronegativity. So there's no two atoms that have identical electronegativity, but there's still a threshold. So technically, like when you connect, like let's say O to S through the bonding, this is going to be polar covalent. But how do I know? It's because you see, when you're connecting any two different atoms to each other, unless they are not carbon, hydrogen, and boron, it's going to create a polar covalent bond. That's it. So I'm not saying like if there is a carbon, boron, or hydrogen part of the bond. I mean, when the only two different atoms that have similar enough electronegativity to each other that we technically consider electronegativity to be the same are carbon, boron, and hydrogen. So these are the only guys that are going to be creating. So there are like different atoms, but when they connect to each other, they're going to create non-covalent bonds, non-polar covalent bonds. But let's say anything. Let's say like phosphor reacting with chloride. Like chlorine. It doesn't matter. I already know it's polar covalent bond. I already know that because I know the only exceptions. You see, chemistry is full of exceptions. You need to know the trend, and you need to know the exceptions, so you don't have to memorize individuals. That's how it works. That's how studying like in a smart way works. So, okay, so let's get started. So polar covalent bond is a bonding between two atoms of different electronegativity. So it's bonding between any two different elements unless it's a bonding between hydrogen, boron, and carbon. That's it. You see, it's pretty simple. So, and then we're gonna talk about like all those so now we're gonna talk about like, for example, there's something called net dipole. We're gonna talk about like partial charges and all of these informations. So you see, polar covalent bonds lead to two things: net dipole moment, which is drawn like an arrow like this, and two, create partial charges. And by the way, these two are connected, so they're related. So we can draw both of them on the same thing. So it's actually pretty easy. So you see like how to draw the net dipole moment. It's very easy. The arrow points from the less electronegative atom to more electronegative atom. Done. So you won't believe me? Well, let's say we have a carbon with CL. Again, this is not a Lewis structure. I'm just giving you like an example, like the one that you guys probably will see on your weekly quizzes. So, which one is more electronegative? In other words, which one is closer to F? You see, it's very easy to compare because we talked about like F is the most electronegative one. Well, Cl is here and carbon is here. Clearly, Cl is closer, so Cl is actually more electronegative. So the arrow will be pointing towards it. That easy. So it's just showing you where the electron clouds are moving towards. Because this guy has an electron cloud, this guy has an electron cloud. There's an electron here and there's an electron here. But this guy's electron is, even though it's still being shared with this guy and this guy's electron is being shared with this guy is gonna like, yeah, I'm gonna have a little bit of yours more than you're gonna have mine. So that's literally what it means. So there's like this arrow is pointing towards Cl. That's what it really means. So guess what? When you're actually tilting electron cloud towards the Cl, that's going to come with consequences. And what consequences that? Watch out. You see, we have partial charges. So you see, it's actually not full charges that we have seen with ionics, because again, nobody takes the other guy's full electron. It's more like tilting towards the other person. So in polar covalent bonds, the more electronegative atom becomes partially negative, and the less electronegative atom becomes partially positive. So let's use our example earlier. So so carbon with a Cl. So we already know that the dipole is actually pointing towards the Cl. So that literally means that the Cl is going to have a bit more electron and carbon is going to have a slightly less electron cloud. So that makes this guy, so this is like, you don't draw like a charge like this. That means it's a full charge. You draw like something like this, the negative. So that means it's a partial negative, and this becomes partial positive. Can you draw both of these net dipole and these things? Again, yeah, I mean, they literally mean the same thing. So they're like, doesn't mean like when you draw one, you don't have to draw one. This really depends on like what the question is asking. But the question is as simple as it gets. It's pretty simple. Yeah. So let's do like another example, and then I'm going to pause for a second, and you guys like try to do it before I do this again. So that would be, let's say, so carbons, no, let's say oxygen attached to a hydrogen. So pause the video here. So I'm gonna start writing the answer right away, but you pause it here so you get a chance to do it before I complete this question. Because remember, guys, if you guys just watch me do questions, you're not gonna learn. Remember, not only you have your self-confidence goes up when you do questions, you make the mistakes that you would have done on the exam during your own time. And also, the more practice you do, the faster you become. Because remember, if in order for you to do well in a UBC, it's just not knowing how to do a question is not enough. You need to be able to do it very quickly. Time is a huge essence. So which one is more electronegative? Well, I mean, you should know, but okay. So oxygen is like almost like one of the most electronegative elements in the world, and hydrogen is like, come on, it's like really. So what happens is, so obviously hydrogen is a lot less electronegative, so it's gonna, the arrow is gonna point towards this. And then the hydrogen becomes partially positive and the oxygen becomes partially negative. Beautiful, isn't it? I know. So that was for polar covalent bond. What about non-polar covalent bond? Well, when you know which one is the polar, well, it's kind of it's very easy to tell the non-polar one. What will we have to cover? So non-polar covalent bond, it's a bond between two atoms that have identical, well, when I say identical, means like two same atoms, because nothing really have the same electronegativity unless you're actually the same, like O2, for example. So identical or very similar electronegativity. So yeah. So have identical or very similar electronegativity. So again, who have very similar electronegativity? We already mentioned earlier. It's carbon, hydrogen, and boron. So let me give you an example where we would actually label bonds as covalent, like polar covalent bond or non-polar covalent bond. By the way, today we're going to actually do Lewis structure, but not entirely. Mostly it's going to be the next video and next class is going to be how we cover the Lewis structure. And attending, like watching that video is going to be super helpful for you guys. So, okay, so carbon, hydrogen, boron. So let's say we have this question. Of course, again, don't ask me like how I draw this thing, because well, because we haven't covered the Lewis Lewis structure yet. So we're gonna get there, don't worry. So what are we gonna do? We're actually gonna use different colors to label these bonds. And of course, if we have polar covalent bonds, we're gonna also use net dipoles and partial charges. We're gonna give it to all of them. And it's actually, you'll see, it's actually not that difficult. So again, I'm going to use, so we're going to write red for polar, and I'm going to use green for non-polar. So I'm going to actually label these I'm not gonna just like point at them. I'm gonna just paint over it, and that's how it's gonna be. So, so again, pause the video right now and then try to answer this question. Okay, so you see, like right away when I look at this, again, what is my mental approach as a person who's been tutoring this and has a lot of experience is this. That I told you, my approach is to find atoms that are different than each other. And I look at it and we're like, well, everyone is different. So, okay, that doesn't work. Okay, never mind. So I need to find, in order for me to find the polar ones, I need to find any bond between two different atoms but those two different atoms cannot be boron, carbon, and hydrogen. So I'm only going to be focused on polar ones. So yeah, well, yeah, there you go. Carbon and oxygen, those are different. Oxygen is a lot more electronegative than oxygen. Look, also, boron and chloride. Oh, by the way, I forgot the lone pairs. By the way, when you go to Chem 123, you don't do lone pairs anymore. So that's why I keep not putting the lone pairs, because you're going to have to expect them. But anyways, and so yeah, so this would be, whoops, this would be also a polar covalent bond. And I think that's it. Yeah. So, and then also draw, so let's actually draw the net dipoles. Oxygen is more electronegative than the carbon, so it's going to be pointing in this direction. And also same thing for this one. It just was a coincidence that they were both pointing up, but yeah. And the chlorine and oxygen, they're both more electronegative than the boron and carbon. Again, how do I know? It's because I've done this for a while, but again, so when you open the periodic table, both oxygen and chloride, they're very close to the fluoride, while the boron and the carbon, they're so far away. So obviously, as we said, the electronegativity increases as we go towards F. So it actually causes these guys for the chlorine to become partially negative, boron to be partially positive, and oxygen to be partially negative again, and carbon to be partially positive. And then again, it's kind of like when you say it's all of these guys are belong to this group, then everything else belongs to the other group. But let's look at it. I told you non-polar covalent bonds are pretty much the ones that have similar electronegativity, or so they have to have identical electronegativity. Let's say, for example, O2. So you see O2, even though O's are very electronegative, these two, so it's like diatomic molecules. All of diatomic molecules are nonpolar because they have the same electronegativity. But when it comes to different atoms, carbon, hydrogen, and boron, when they're attached to each other, again, you see, like we saw carbon with oxygen, that was like different. That actually causes, so when they're actually the carbon, hydrogen, and boron, when they're attached to each other, their electronegativity is very similar to each other, and that actually makes it non-polar. So all the rest of the bonds is like that. So beautiful, isn't it? Okay, now, so that was that. Now we're going to move on to another topic, which is Lewis structures. So, by the way, I personally can't get enough of chemistry. And by the way, I can't hear it enough. Like how many people tell me that, yeah, I used to love chemistry in high school, and then I came to university and I hate it now. Well, to be fair, like anything you learn in high school is very very easy. But when you get into university, that's the real level that you need to know. So, but to be honest, like as long as you know what to look for in different types of questions, nothing is really difficult, especially in these levels. Of course, there are like some like organic chemistry you could consider to be a bit difficult, but not really. So yeah. So Lewis structure. So by the way, as you will realize, that my method is totally different than the method that you learn in CHERP. So like they have nothing to do with each other. Like I don't count all the electrons that you're gonna find in something. That method, in my opinion, is like way too slow. And like you're gonna have like multiple choice questions on your exam where you have to draw 5 Lewis structures in 1 minute. Why in 1 minute? Because that's the technically amount of time that you have, maybe less than 1 minute, the amount of time you're expected to have for one multiple choice question. So that wouldn't work. Like that method of that, which is pretty slow. My students can answer like draw those structures in less than 10 seconds. So that works. So you need like you'll do it in 50 seconds and you still have like 10 seconds to check your answers. So that's how it works. Okay. So Lewis structure is pretty much is like how predicts theoretically how the atoms would bond to each other in terms of how many lone pairs they would have and how many bonds they would have with each other. So they would meet a certain number of criteria. And those criteria that we're going to talk about today are octet rule and formal charge. These two rules must be met for most of the situations that we draw. And you're like, what do you mean most? Well, again, exceptions. So when it comes to Lewis structure, one of the 2 rules that are very important and you need to be able to draw, like you need to be able to like check for when you're done drawing your Lewis structure, or when you're drawing your Lewis structure, you have to 2 very important rules are octet rule and there is the formal charge, which is actually the charge that you were seeing in ionic bondings. It's the same thing, but we were just not calling it formal charge. We were just calling it charge, but it's the same thing, literally. So before we get to the octet rule and formal charge and what the difference are and all of that information, let's actually talk about what is the octet rule. So you see, the octet rule is about, okay, we already know, by the way, this is all for covalent bonds. So it's about the bonds that actually involve sharing electrons. So octet rule says oct means 8, means it's a rule that is about 8. But what 8? It's about, okay, so if you count all the electrons that you expect to have after you're bonding with other ones, so the electrons that belong to you and the electrons that are shared with you through the covalent bonding, it should add up to 8. That's what octet rule says. So it means, so after completion of bonding, the number of your electrons, like the ones that you belong to you, like lone pair electrons and the electrons that are right next to you, your electrons plus, plus the number of shared electrons with you should add up to 8. So what do I mean? Let me just give you an example. Of course, I'm not teaching you Lewis structure yet. I'm just giving you an example like how it works. So for example, like when a carbon is attached to, like, let's say 4 hydrogens. So you see, so you need to know this, that every bond involves 2 electrons, one from each atom. Well, the electrons that belong to the carbon, like itself, it belongs to it, are these 4. And the ones that are being shared with it are the hydrogens. By the way, the polar covalent and non-polar covalent is not relevant when it comes to this. Everyone is technically sharing stuff with each other anyways. So you see, it does add up to 8. So this structure meets the octet rule. This is just an example though. So let's change it up a little bit. So imagine like if so a nitrogen attached to so let's say something like crazy looking like this. So by the way, we have to check the octet rule for everything. By the way, hydrogen never reach octet rule. That's just an exception. Like that's literally impossible to do so. So, but let's say actually we're checking the octet rule for nitrogen. Again, we don't do it for the central one. I'm going to do it for oxygen too. So that's not a difference. So we're going to count the electrons that belong to itself, like the ones that are right next to it. So it's going to be 1, 2, 3, 4, 5. 5. And the ones that don't belong to it are going to be 1, 2, 3. But these are technically shared with it. Again, what do they add up to? 8. So again, this rule, again, hydrogen. So the hydrogen, so let's count for the hydrogen. Hydrogen has 1 and it's being shared with 1. So it adds up to 2. It always adds up to 2 for hydrogen. It never reaches octet rule. And let's do it for oxygen. Oxygen, so it's like 1, 2, 3, 4, 5, 6, 7, 8. So it meets for the, so you see this structure that I just made it up. I don't know if it actually exists. Meets the octet rule. So that's how you count. Again, I haven't really started like teaching you guys the structure, but it's one part that is very confusing for everyone is how you count the octet rule and how it is different from formal charge, which I'm about to tell you. So most people struggle with loose structure is because they confuse how you count for the octet rule and the formal charge. That's the problem. So you see, again, we're going to talk about like not everyone meet the octet rule, but we hope for meeting the octet rule. There are some that must meet the octet rule. There are some that don't have to. There are some that never do. And we'll see all of them. So let's do this. So what about formal charge? How do we know like if something is so how come these guys didn't have a charge? Actually, they didn't, but I mean, I'm gonna actually give you the formula for formal charge. And I'm going to give you some analogies and techniques to remember it. But the reason you are this is like this, like it's neutral. I'm going to explain it in a second. So formal charge. So formal charge is actually the charge that you carry, but how do you count it? So I'm going to actually explain. So it's the number of valence electrons you expect to have. I'm going to explain what it is. Minus the number of electrons that belong to you in that structure. So you see, it's really about how many you're supposed to have minus how many you have. But we don't count the shared ones. We do not count the shared electrons. Not the ones that it is sharing, the ones that is being shared with it when we're counting how many electrons it has. So that's the significance of it. So let's try. By the way, oh, you wonder, okay, how do we know like what the expected valence number is? Like, how many electrons do we expect to have? By the way, when we're talking about like an atom and all the bonding and stuff, nobody cares like how many electrons it has in total when it comes to bonding. We only care about the electrons on its most outer shell, which we call valence electrons. Because those guys on the most outer shells are going to be the farthest away from the nucleus, and they can actually go like and interact with other atoms. The other ones are under too much gravity to be able to do much. So that's why like we only care about the valence electrons. But you're like, okay, so how do we actually figure out, okay, so we know we're supposed to know like the number of the expected valence electrons for all the atoms, and it's actually very easy. We need just a periodic table. So you see, the valence electrons, the expected valence electrons that you have for any atom actually belongs to, like it's the same as the group number. But for these double digit ones, which are like 13, 14, 15, 16, 17, it's just the lower digit one, which is like 7, 6, 5, 4, 3. So you see, for example, it doesn't matter where you are down these lines. Like calcium, again, let's forget about the charge though. If it is neutral, and so it hasn't lost the electrons, it would have 2. It would have 2 valence electrons. Like boron has 3, gallium has 3 and 2. So that part is not different. All of them are different. So these guys, since they belong to the same group, they all have the same valence electron number. So these are 4, these are 5, these are 6, these are 7, and these are 8. By the way, noble gases, they're called noble gases because they, in reality, they're happy and they don't react with anyone. But in theory, they could actually bond. And we actually draw their Lewis structures bonding to different atoms. But again, that's in theory. They're very, if you're happy to be on your own, why would you react with someone? That doesn't make sense. So now let's do some practice. So let's do the examples, like why the structures that I drew earlier, how they have 0 formula charge. So a carbon attached to 3 hydrogens. So you see, again, if you actually look at the periodic table, carbon is on group 14, so I expect it to have 4. Now, how many electrons do I have? Does it belong to? How many electrons do belong to this carbon? Well, the ones that are right next to it. So you see, I'm not counting the shared ones that are being shared with it from other atoms. So 4 minus 4 is 0. So that makes sense why it's neutral. And for the hydrogens, it's actually, look, so it only has 1. And which group does it belong to? Group 1. So 1 minus 1 is equal to 0. Easy. Now, so let's look at the other examples. So nitrogen double bonded to an oxygen and with a hydrogen. And there's a lone pair, there's a lone pair, and there's a lone pair. So this one has a lone pair. So which group nitrogen belong to? 15. So let's say 5. How many electrons do you actually see it belonging to itself? Not shared ones again. So these are like 1, 2, 3, 4, 5. Oh, so that's 0 again. What about oxygen? Oxygen belongs to group 16. So that's so 6 minus, how many does it have? 1, 2, 3, 4, 5, 6. So that's 6, so 0. But you see that my problem is that my students tend to confuse, like at the beginning at least, like because when you do drawing those structures, you have to meet both of these things. Like whatever the charge is, again, you're like, oh, does it have to be 0? No, but it has to be the charge that you expect it to be, and which we'll discuss. So what happens is, I personally use this circle like method to just remember which one is which. You see, for 4 mole charge, you have a very tiny circle, and that this is you only count the electrons within that tiny circle. But for the octet rule, so that's 4 mole charge circle. But for the octet rule, your circle is a bit bigger. So that's octet rule circle. So this is how I personally remember, like, because, you know, remember after like having done this for a long period of time, you kind of know these things, so you don't have to do it to know. So that's why, like, when it comes to me teaching you guys, I personally like use these circles to know which one was which. At least I know there are 2 circles, and then the smaller one is the 4 mole charge, and the bigger one is octet rule. So, but so yeah, this is actually how you count octet rule and 4 mole charge. So let's actually do some examples. Again, we're going to mostly focus on normal charges for now. So yeah. So I need you to pause the video again and try to find out the 4 mole charge. Again, we know hydrogen is neutral. That's like hydrogen is always neutral, so that's not really a big deal. But I need you to find a 4 mole charge for this oxygen, this nitrogen, this nitrogen, this nitrogen. So please do that. Again, remember, like, I'm going to find the answer right away. So if you don't pause, you're not going to see this. So again, how many electrons do we expect on the oxygen? It's 6, group 16. How many electrons do you see around it? Small triangle, small circle. So that's -5. So +1. So it is +1. By the way, I noticed one of my students like making this mistake. We have to put this positive charge. Don't do the math and just let it be. Put the +1 here. Let's do the nitrogens. So nitrogen is actually 15, so 5. So see 5, 5, 5. But let's count how many electrons you find around it. So it's going to be 1, 2, 3, 4. So it's going to be 4. Oh, sorry. So you see, I made a mistake of not meeting the octet rule. So it wasn't meeting octet rule. So 5 minus 1, 2, 3, 4, 5, 6. So it's equal to -1. So it is -1. What about this one? 1, 2, 3, 4. So -4 is equal to +1. And this nitrogen is 1, 2, 3, 4, 5, 6. So again, 5 minus 6 is equal to +1. So +1. So you see, it's actually pretty easy figuring out like what the formal charge is how many electrons you expect to have minus how many electrons you find immediately around it, which could be part of the bonding electrons or could be lone pairs. For the octet, you count all the electrons that you have and the ones that are being shared with you through bonding. Simple. Yeah. Please, again, if you have any questions, just ask me later. That's it for today. So good luck with your study.